Hi everyone, this is a video lecture on free fall. So previously in physics what we've been learning about is how to model motion in one direction mostly. We use the kinematic equations for that, for constant acceleration, and then we can use the other equation, which is velocity is equal to delta x over t for constant motion. So now we're going to look at a very specific type of motion called free fall. I'm going to define what free fall is, what the conditions are for free fall, some of the assumptions we can make with free fall problems, how to break them down. I'm going to show you some diagrams of modeling motion. I'm going to show you some graphing of modeling motion. And then at the end of the video, actually what I'm going to do is make a separate video. I'm going to solve some problems using the concepts of free fall and how to apply them to any system. So as always, we're always looking about how we model the motion of objects. So this is modeling falling objects specifically. So just kind of think to yourself, what kind of motion is an object falling? Is it moving at a constant speed? Is it moving at a changing speed? Is it moving at a constant acceleration? Or is that acceleration changing? So these are some ideas I want you to think about as we start the video. And like I said, this is the stuff we'll cover. Most importantly, the conditions for free fall. So when do we apply these concepts? So we have to identify what is free fall. So I'm going to do that first. And then I'm going to model motion through diagrams and graphs to show you what assumptions are made and how to interpret them. And then we're going to use the kinematic equations to help us solve these problems. And you'll understand what this stuff will mean later. So what will hit the ground first? Is it a piece of paper or a book? So unfortunately, it's hard to do the demonstration right here, so I'll definitely do this in class. But I'll spoil the event. So I think we all know that if we had the two right here, the book will go before the paper, right? So, that was what was known. And the major difference between the book and the paper is actually the mass, right? So originally it was thought that heavier objects will fall faster than lighter objects, until Galileo came along and did his famous testing, I guess, with the Leaning Tower of Pisa. But ideally what he did is he did multiple tests, and he actually found that if he used objects that didn't have a lot of air resistance as an effect, like heavy objects like a bowling ball and maybe like a rock, he found that they actually hit the ground at the same time. So that was really strange, because originally we thought that heavier objects would hit the ground at the same time, but when you take something like a bowling ball and like a rock, well, a rock's pretty heavy, so to counteract the air resistance, it would be actually more challenging than a piece of paper, for example. With that said, we find that all objects hit the ground at the same time, which means that they actually accelerate the same. Now, I use the word accelerate because it's not, if it were a constant rate, we would see an even interval of time and distance as it goes down. But what happened is Galileo found that that wasn't true. He found that as time progressed, the distances actually got bigger. And if they get bigger, it means you're going faster. So things went faster as they went down. So they accelerated. So these are really cool videos. I'm going to show you a few here. I've already kind of timed them out so that they're looking pretty good. So let's see. Watch, here we go. Alright, so I have it as full screen right here, and then let's get rid of the ad. So here's a really cool experiment right now. So this is inside a very big vacuum chamber, which means that they took out all of the air, so there's no air resistance. And you can see here that we have a bowling ball right here, and we have a feather. So watch what happens when we, release the two. I always like this video. There we go. So you can see that the feather and the bowling ball are actually staying together the whole time, which is really cool. Yeah, so it's pretty cool. So this is Brian Cox. He's a very famous physicist. So, like, if you know physics, you know Brian Cox. So that's him in the video, and he's really excited to replicate the experiment that was hypothetical, like taking a bowling ball and a feather. And what better way to do that is at NASA's vacuum chamber, right? So that's pretty cool. So let's go ahead and do this. So the other video I want to show really quickly is actually this one. So this was actually done on the moon, kind of the same conditions. You don't have any atmospheric conditions, so therefore if you have a feather and a hammer, which he does in this video, you'll see that they'll actually hit the ground at the same time. So this is really quick.
I have a feather in my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Yay!
How about that? Mr. Galileo was correct in his findings.
Okay. Let me just get rid of this and then come back to here. Okay, so as you can see, the point being is that if you take away air resistance, you'll find that objects will actually accelerate at the same time. So, what is free fall then? So, under the influence of just gravity, so just the pull from gravity, and no air resistance is considered free fall. So luckily in most of these, about 99% of these problems, you're going to find that we're not going to consider air resistance. So even though we're going to solve the penny problem when you're on the Empire State Building, we're going to allow it to fall all the way down, we're not going to consider any air resistance. In fact, you can honestly ignore it unless they tell you to specifically include it. So we're going to ignore air resistance. So yes, a piece of paper is actually going to go flat to the ground too. So, things that model free fall. When do you start thinking, say, oh, this is a free fall problem? So this is the following condition. So first it has to be dropped, a problem that anything that's dropped. So you can take a ball and you drop it, you have a pebble and you drop it. So the word is dropped, and dropped from rest. So generally when you see that, you're going to have an initial velocity of 0. That's the assumption you can make for those types of problems. So strangely enough, thrown downward and upward are considered free fall. So even though you give it a push, it's after the push that we start modeling it. So yes, there is a force when you start pushing the ball, but you don't push the ball the whole time. You only push it up until you release it. Once you let it go, the force is gone. And once you set an object in motion, it stays in motion unless there's an outside force, and in this case, it's gravity pulling it down. So moral of the story is yes, even throwing it upward works as a free fall object because the only thing that's working on it is gravity. In fact, in most cases, anytime you're in the air, it's just a gravitational force. Now, I'm not an example of free fall, which you're probably saying, yes, I know, but since gravity acts in all things, you can ask, why aren't I free fall right now? Well, I am being acted upon by another force, even though it's not air resistance, but the table and the chair, the floor and the chair are holding me up. So I'm not considered free fall because I'm not under the influence of only gravity. So it has to be only gravity. We will actually go into the throne at an angle, but we need 2 dimensions to model that motion, so I have a whole new method for that. But technically, yes, that's considered free fall. So anything in the air, basically, is free fall. Up, down, dropped, all those things. Things that do not model free fall, well, these are going to be considered, like, for example, things that have a huge air resistance effect. Anything light, so like a feather, or a coffee filter, or a paper, or anything else you can think of that might be troublesome. Most of lab will always use heavy objects to reduce the air resistance effect. But if you use like a styrofoam ball, for example, well, that's actually going to affect your values quite greatly. So that's one way you can, point out the air resistance effect, or see the air resistance effect. The key word is terminal velocity. So you might have heard that before, but that's when the pull down is actually negated by the push-up from the air resistance. When that occurs, you no longer accelerate and you keep your velocity. So that's what's called terminal velocity. Skydivers reach terminal velocity. Technically, the penny, if you drop it from the Empire State Building, will reach terminal velocity. All objects will reach this terminal velocity because the air will push up on the object, air resistance, or drag, if you look more specifically, in a more engineering kind of way. So if you see that word anywhere in physics, first of all, not free fall. Second of all, that object is going to be moving with a constant speed, so you need to use the constant motion equations for that one, not acceleration. Acceleration would equal 0 in that case. So terminal velocity. Also propulsion. So anytime you're being pushed through the air, and the biggest examples of that are things that are already have engines in them. So like airplanes and rockets. Not projectiles. Notice I didn't say like a dart gun. If I had like a dart gun, like a Nerf gun, and I, shot it, that's not, that is free fall for the most part, because after it leaves the dart gun, the force is gone. So that's considered free fall. So when I say propulsion, I mean things that actually push while it's moving, like rockets and engines and airplanes, so all those kinds of things. These are very vital and important for modeling problems. You just know the difference between free fall and not free fall. Good news is most of the time this is going to be your case. You're going to be dealing with free fall, but look out for those tricks, right? There's always something in the problem that might trip you up, so these are the things to look out for. And also when you're doing lab analysis, it's really important to understand that unless the object is really light, you're not going to have a big effect from air resistance. Okay, so objects under the influence of gravity will actually accelerate, strangely enough, at a constant rate. That's actually just really cool. That means everything on this Earth will gain speed as it falls the same way. Awesome, isn't that amazing? And not only is that amazing, it's a measurable value, and the value is 9.81 meters per second squared. So, first of all, that means how, no matter who, if we all were to stand at the edge of a building and safely jump off and land, I don't know, on pillows or something, we're safe. We're always safe in physics. If we all jumped off and no huge air resistance is considered, we'd all gain speed at the same rate. That's really cool. About 10 meters per second. So 10 meters is about a story. So it's pretty fast, actually. It's 32 feet per second squared. Now, acceleration is a vector, so we have to model its motion. And since we usually call the upward motion positive, gravity, since it's being directed downward or toward Earth, is going to be modeled with a negative sign. But keep in mind, this value is positive. Like, this is a positive value, but the sign tells us the direction. So we're always going to use a downward direction with a negative sign. So just a little more about what this means. How fast you're gaining speed. So this is pretty crazy because in the first second you fall 1 story. In 1 second, that's how far you fall. And you're going about 32 feet per second. And then the second you're going 20 meters per second. You fall like 2 stories. And then the next second you'll fall 3 stories. So I hope you see like craziness in this. So the more you fall, the faster you fall, and the more speed you gain. It's pretty amazing. So for 1 minute, for 60 seconds, what is that? That's 10 times 60, so 600 meters per second. That's pretty crazy. You're going, if you're falling for a minute and no air resistance, you're going twice the speed of sound. I mean, that's just so crazy, right? So that's what this number means. You're speeding up over time. So I'll demonstrate this in class, but I will take a motion detector and actually let something fall in front of it. And spoilers, you'll find if I take the slope of a velocity versus time graph, that is by definition the acceleration. So if you see the slope, 9.792. That's really cool. So that shows you that the 9.81 is pretty close. And then you can see right here that the acceleration is relatively constant, which is exactly what we said. So these are the motion graphs for that. So if free fall is constant acceleration, then we can use constant acceleration equations to model that. So turns out that we're going to just reuse these instead. Well, not instead, but just in addition to what we know about acceleration already. But the thing that's new, this is the new part of this, because this is not new, the equations we've seen before. What's new is the fact that A is implied when you have a free fall problem. They won't give you this value. They assume you will recognize it as a free fall, and you can make the assumption. So I put the negative sign there because unless it says otherwise, we're going to assume it downward. So all these A's are known. And that's the biggest difference in what we did earlier versus now. We know acceleration for all problems. So this is actually kind of repetitive, so I'm just going to go ahead and move forward. So, you know, some keywords like if you drop or if something falls, you can make the assumption that the initial velocity is 0. If it's not dropped or it fell, you must use the value that they give you to throw up or down. So if you throw up at 5 meters per second, use positive 5 meters per second. If you throw down, then you have to imply the sign, so negative 20 meters per second. Okay, so yeah, sure, I'll model this problem, why not? This is a straightforward one. I can keep this in this video. Just give me a second while I just establish a few things. So I'm just connecting my thing right here. So let me just, yeah, it's yelling at me. All my things that are open. Workspace. Just gonna take this and just put this right here, sorry. There we go. Alrighty, so here's the problem, right? So this is a standard problem. So imagine you're on the Empire State Building like this, and you're standing on the top, although you shouldn't do this anyway, but let's pretend. So you drop a penny at the top of the Empire State Building. Let's assume that we know the height of the building. Just like this. The question is, without air resistance, how fast will it be traveling at the bottom? And then how long does it take to fall? So T. So VF and T. Okay, so first off, let me just make one quick distinction, because this always throws students off. First of all, the final velocity when it hits the ground, by the way, is not 0, which you're probably looking at me like, what? It stops when it hits the ground. Well, you're right, it does hit the ground, but we want to model it in free fall, which means, you know, if this were an up-close view of the bottom, so this is the ground here, we want the speed right before, sorry, it's a terrible penny, right before it hits the ground, because this is when free fall is modeled. Think about it. As soon as it hits the ground, so just like a separate thing, as soon as it hits the ground, it's going to actually undergo a different acceleration that's caused by hitting the ground. So it's not going to be 9.81. So if it hits the ground, it will have whatever speed it has right before, but then it will go to 0. But this change is not g. So actually, if you wanted to solve that, that's a totally different problem. So first off, do not assume that the final velocity is 0 when it hits the ground. You always assume right before it hits the ground. Alright, so let's finish this problem. So it looks very empty, right? It's like, oh, we only have like a distance. So we do have a delta x. Now notice that this object's actually moving downward, so the displacement is actually negative 381 because it's moving downward. Now since we dropped the penny, we can assume that we have the initial velocity as 0. A lot of students think there's not enough information in this, and there is. You just have to take it out. You have to reorganize it and recognize it in a different way. So notice we do have VI, strangely enough. And the next thing you have to assume, strangely enough, is the acceleration. This thing is being dropped, there's your key word, which means this thing is undergoing the acceleration due to gravity, which is g. G is negative 9.81. Well, g is 9.81, but to model the direction, it's going to be like this. So the acceleration A points down. And we have the initial velocity 0 up here, just like that. Okay, the first question is asking how fast, right? So the best equation, kinematic-wise, is this one. Now I'm going to change this to delta y because technically this is a vertical measure, right? I know I actually labeled this as delta x, so I'm going to just be consistent here. It's fine to use x, it's really not a big deal, but to really model this, it's actually a change in a vertical measurement, so that's why I'm going to do that. Final velocity squared equals the initial velocity squared times 2, negative 9.81, times negative 381. I'm going to put the negative in, don't worry. Now this is very important. If you don't follow signs, you're not going to model the situation. So when you solve this out, because I've done this a couple times, you get about 86.6 meters per second when you solve it out mathematically. This is the magnitude of this speed. The magnitude of the velocity. So in other words, this tells you how fast it's going. But in the calculator, since you squared this, you actually have to go back in and put in the sign to model the fact that it is moving downward at that point. If you leave this as positive and you're saying it's moving up at 86 meters per second, which doesn't make any sense. So you must put the negative there to model what's going on. So that's pretty fast. This is about 130 miles per hour. Actually, I think it's more than that. I think it's 180. But anyway, point being, it's very fast, right? So if there was no air resistance, this penny actually would be would be lethal because of the speed. It's very dangerous. But just kind of a side note on this, it actually reaches terminal velocity about right here. So, and it reaches 60 miles per hour, which is not a lethal, it's not a comfortable speed, but it's not a lethal speed. So, moral of the story, in real life, you couldn't actually do any damage to people. Please don't ever do this, of course. I know this is like an interesting problem, but just to show you how fast the penny would go at the bottom. It would go pretty fast if you didn't have any air resistance. Now, how long was it in the air for? Well, technically, we need to, I'm going to do this a little redundant, but to show you, I need the information that models that question. So, how long would be from here to here, right? So basically, the whole trajectory right here. So it turns out that all this information transfers over. Again, I'm being repetitive. You don't actually have to ever, do this, but that's okay. It's the same height. It's the same acceleration. It's actually the same initial velocity since we're dropping it, and technically we can use the new information that we got from the problem like this. So let's go ahead and model the situation, and we're looking for how long it takes to fall. So the best equation, although there's multiple ways to do this, would be the following, where we have negative 86.6 meters per second. This is 0 because that's the initial. And this is what you get for that. So if you solve this out, this is about 8.81 seconds when you solve it out. Now, it might be a little different if you use these numbers because I'm actually just doing this from memory. If you calculate out, you might get 86.4 or 86.5. It's fine. The method is the most important part. So 8.81 seconds. So that's a long time to fall. Like if you think about 8 seconds, it's starting, I'll tell you 8 seconds right now. Ready? Go. 1, 2, 3, 4, 5, 6, 7, 8. That's crazy, right? Like, imagine falling for 8 seconds. That's a long time. So a penny from the Empire State Building would fall for 8 seconds. So crazy. Learning lots of things today, right? So moral of the story. These problems are very empty, right? So you have to make assumptions and imply information. Especially this assumption. You must always make this assumption. This is always true for free fall, FF free fall like that. So anytime you have a free fall problem, you are given the acceleration. So that's the good news. It's actually simpler in that sense. Okay, so what does this look like? Back. Okay, so what does a dropped object look like on a position, velocity, and acceleration graph? These are all important pieces of information. So as a kind of exercise, pause the video now and see if you can predict this. And don't skip this part. It's actually so important that you actually pause the video and try this out. So I'm going to take a quick pause for you to do that. Okay, I assume that you paused the video and tried this out on your own to see what you can predict. So, before I show you the answer, let's think about what's happening. An object is going to start off at rest and gain speed. And if it's falling down, it's going to gain speed in the negative direction. So, to model that, no speed is a flat line. So we start off at rest. My drawings are not great, so just, be okay. But then we're going to gain speed, but we have to go downward to model the downward motion for a position time graph. So it's going to look like this. Remember that this is a speed up, and the negative slope means backwards or down, because we have a steeper slope here than there. So we start off at a 0 velocity. And then we would move with a constant acceleration that's speeding up. So this is a speed up, remember? This is a speed up backwards or down. And this is my favorite because it's constant. And this value, since it's free fall, will be negative 9.81. Negative for the direction, and then the value is constant. Ta-da! That's what you have there. Now here's a new one, right? What does an object look like when you throw it up and down, right? I'm going to do this one for you. You could try actually. So you toss an object up and it comes back down, okay? How would that look? Well, something like this. You would toss an object up, so it's going to gain a positive position. It's going to actually stop, right? And then lose its position, right? This would go up and come back down. This is me if I did this, right? So that's what I just modeled there as position versus time. You gain distance, and then you lose distance. You come back to where you started. But let's analyze this, right? This is a steep graph. So and it's positive, so this is a positive steep graph, so you're going pretty fast here. But notice that the slope goes to right here, which is 0, right? And that means you're at rest. You start off with a positive velocity, and you go to rest. Roughly a little before, maybe to make it easier, I'll just put it in between 5 and 6. So, and then here, notice the slope changes, which means you have speed, and then you have a speed up here. So, positive velocity to 0, 0 to negative velocity. So that would look like this. Positive velocity to 0 about here, right? That happened about at 5 seconds. And we're slowing down, so it'll look like this. Negative velocity and speed up. Now this thing is what I call symmetric, which means that, sorry, it's another M there, that's okay. Symmetric meaning it's going to have the same value of the slope as this side as this side. So this slope, if you notice, is the same as that slope, conveniently because it's the same acceleration here. So this is what an object's graph looks like if you throw it up and then have it come back down just like that. So I have a better drawing here. This is a little nicer. But these are common graphs, especially if you're doing AP. This is a common AP graph. They want you and expect you to read and recognize. But notice that this is exactly what it's doing. It starts off going fast, stops, and starts to speed up back down. So this is a slow down as you go up and a speed up as you go down. Slow down, speed up. And that's exactly what these graphs model. So there's some more things that we can model too with an up and down. So some assumptions that you can make. So I recommend that you draw this diagram. If you need a minute to like pause the video, I would do that. So I'm just going to make up numbers for this just to model the assumptions that you can make for an object that's thrown up under free fall. So this is for free fall only. So let's say that time is 0 right here. We can always, so these are the assumptions. I'm just going to write that note. Assumptions we can make. We can always assume the acceleration at any point of this is negative 9.81. Negative meaning down, so if I were to draw a vector diagram, this imagine is a ball. Now I know that this object's kind of curving, but this is really an object just going up and coming back down. Now I opened the curve out so it wasn't like on top of one another, because really what I'm talking about here is a ball going up and a ball coming back down. So you can see how confusing that is. So I just spread it out just so it's a little more clear on what's going on. So the acceleration vector would be pointing down as 9.81. Actually, when you do it like this with an arrow, you can just use this direction of that instead of a sign. So this would all be 9.81. I don't want to write on that thing. So this red represents the acceleration vector. So what we can assume with the blue, I'm going to make up a speed, these numbers won't work, okay? Let's say this is 5 meters per second, we throw it. Now since we're throwing upward, the velocity vector will look like that. And what I mean by vector is the arrow, of course. I'm just going to put a positive here to emphasize that it's moving upwards, so it should be positive. At the very top, the very peak, it does stop. It's very, very brief, but watch. It's not perfect. But we can assume at the very top, the velocity is 0. And notice that the vector, if it's 0, doesn't exist, right? So there's no velocity vector at the top. And let's make up a number here. Let's say it takes 2 seconds from here to here, okay? So it's symmetric, meaning that it's under the same force and goes up the same distance as it comes down. If it takes 2 seconds to come up, it should take 2 seconds to come down. So the total time for this would be 4 seconds. If it's up is going to be 2 seconds, the down will also be 2. So you can make these assumptions for solving problems. which is really nice. And this is the total. The other assumption you can make, which is really helpful, is assuming you catch it in the same spot as you threw it, that this is the same level, the velocity which you catch it will be the same. So the velocity vector will be pointing down in this case like this, and it will be -5 meters per second. So look at the change of the velocity vectors, right? A is always pointing down, and the blue vector models the motion. It moves up, stops, moves down. So I hope that makes sense. And this assumption is really helpful because, and the reason for this is it goes up to some delta y, and it comes back down the same distance. It goes up with this acceleration, it comes down with this acceleration. So we're keeping things constant. So yes, we can always make this assumption as long as it returns back. So a side example, if you have somebody on a cliff and they threw it up and it does this, right? And we know, say it's 5 meters per second they threw it at. Well, what we can assume is at this point, the same point at which they reached it is also 5 but negative. So notice that this speed would not be the same because it had more time to fall. This does not equal 5 meters per second. This is wrong. But we can safely assume that this location is -5, and we can safely assume at the very top the v is 0. Which means, as always, that we have more assumptions or more information than the problem might seem we have. So we're going to use this to help us solve a different type of problem, an object being thrown up. So we solved the dropped ones. Those are not bad. Those are usually pretty straightforward, but these, much harder, right? That's what this diagram is, and this is what this graph is for the most part. So look, they use different numbers, but you'll see the same patterns, right? Plus 20, -20, plus 10, -10, 0 for the velocities. And then the other thing is, notice same thing. They took 2 seconds to go up. It'll take 2 seconds to go down. So I hope you notice that. These are all the things I already talked about in words. Also, another thing I want you to look at is, look, at 1 second we're at 15 meters. And at 3 seconds we're at 15 meters. Pretty interesting, right? At the same position we have 2 times. So that actually comes from the fact that this equation is quadratic, right? Which means when you solve a quadratic answer, you'll have t1 and then t2, which means you'll have 2 times. And it turns out that that's true because you can have the same delta y, the same position, at different times. So usually t1 is the upward motion, and t2 is the down motion. Another cool fun fact about physics. Physics is just so cool. I mean, that's awesome that this equation models real life, right? Being in the same position over time. Pretty cool. So just a warning too. Look at this. At 4 seconds your distance is 0, and at 0 seconds your distance is 0. So, interesting. If you use 4 seconds in this equation, you'll get a d of 0 because it didn't change spots, okay? That's a cool trick. If you know it returns back to where it started, you can actually use the quadratic to find the total time. Quadratics are just more complicated, so I usually don't use them, but you can. So there's, some information with that. Okay, so I'm actually going to end the lesson now, just because I covered all the things that you need to know at this point. The next video, I'm going to model this question and a few other questions that I have here, just so you can see how the complexities come about Each of these, as you can see, actually, this is like the most straightforward. This gets harder, and this gets harder. So the next video, I'll model how to solve these, but you have the basis at this point of free fall. Just to recap some of the things that we did just now, things that you need to know. So free fall recap, summary. Remember that free fall is only gravity and no air resistance. All objects, I'm being lazy, sorry, fall at a constant acceleration, not speed. People confuse this. That value is going to be 9.81, but we model it downward. Remember that you make many assumptions during free fall, including the initial velocity for dropped is 0, that A is always given. If you catch the ball in the same spot that you released, the velocities are the same, but one will be positive for up and one will be negative for down. And that we cannot assume that the final velocity, I'll put this, the final velocity of an object hitting the ground is not 0. You have to do it right before it hits the ground. So those are some of the major ideas. And then remember, the last point I want to make is that you have to use the kinematic equations, right? Because they model constant acceleration. So, turns out that you don't have new stuff. You're just going to reuse the old stuff in a new way. So that's the good news. So you get really good at kinematics now. If you weren't before, now you're really going to get good at it. So I hope that you felt comfortable during this, and if you have any questions, you can always see me. And then in the next video, I'll start solving some new problems. Have a nice day.